Okay, welcome IB students. Today we're going to talk about chemical bonding. So we're going to start off quickly talking about ionic compounds so that we can get into the real meat of the chapter, which is covalent compounds. So first, before we do the basic stuff about ionic compounds, let's talk generally about what an ionic compound, what a chemical bond is. So when I think about a chemical bond, it's always the forces of attraction that are holding elements together in a compound. Now these are always what's known as electrostatic forces, meaning that there's opposite charges, positive, negative. Now these form because elements are trying to become more stable, and generally when you form a bond, you are releasing energy. And in a chemical reaction where you break some bonds and form other bonds, you are trying to overall reduce the total amount of energy that you have in the system. Now it doesn't always work that way, but we hope that it does. So again, they form to lower the potential energy. Now, what are these electrostatic attractions? I put positive, negative. So they could be between particles like ions. They could be between a positive nucleus and the negative electrons between them. But either way, what you'll see is that there's always this electrostatic force. Now, what we talk about in chemistry is, the Octet Rule, trying to form ions or trying to share electrons until you have 8 electrons. Now, it turns out what you'll see this year is that the Octet Rule is sort of a lie. It's good for certain atoms like nitrogen, oxygen, fluorine, carbon, but it is not generally adhered to when you get into other types of molecules. And so we'll get into that. But you should know how to draw Lewis structures. And notice what I do. If this was X, this would be like lithium. Lithium's first valence electron, I put the S electron up here on the top. The next one, if this was beryllium, would have the 2 S electrons there. And then when I would go to boron, I would start to fill around the P electrons. And notice what I'm doing. If I go to carbon now, 2s2, 2p2, now I put the 2p electrons separate. And this is because I'm trying to adhere to Hund's rule. Here I would have nitrogen with its 5 electrons, and then we'd have oxygen, and then we'd have fluorine, and then we'd have xenon or argon or neon. Okay, so when we do an ionic bond, when we look at the compound, we want to be able to draw the correct Lewis structure for this. And so to do this, I first write the correct name. I first use the name to write the correct formula. So for example, if I had something like, sodium oxide, if I was given the name, I'd have to know Na is plus, O is minus 2, so together they form Na2O. Now I separate out the ions and I use the subscripts as coefficients. Na would have a 2 in front, O, you could put a 1, but you don't have to. Then for step 3, I put the charges in, 2 Na plus, and then O minus 2. And then, to save time, I put brackets around the O here. I'm not going to rewrite it. And I give the non-metal, which is O, the octet, and brackets. And so overall, what I'm left with is this. 2Na plus O in brackets with 8 dots, and a -2 or a 2 negative outside. So we can practice some of those in class, but that's the general idea behind the ionic bond. Something that you didn't really talk about last year was the energetics, the changes when you form a bond. You talked about it kind of briefly, how like when you form a bond you release energy, but there's a big part of the AP curriculum where they talk about something called lattice energies. And lattice energies, basically it's the energy when you go, if I show you this diagram down here, the lattice energy is when you go from a solid ionic compound and you change it into gaseous ions. And they show that here, that's the lattice energy. That's the energy required to move from the solid state up to the gaseous ionic state. So that's the lattice energy. they have the reverse of the lattice energy here. Oh, I see what they did. So here's the reverse of the lattice energy here, and then they're showing you the lattice energy here. Now, you could apply Hess's law to this, and this is actually called the Haber process over here, or the Haber cycle. And what happens with this is they're showing you how you can go through these steps, starting with just your solid Na, and your gaseous chlorine, how you could go through the step of changing Na to a gas, go through the step of breaking the Cl bond, go through the step of forming an Na plus ion, go through the step of forming a chloride ion, and then finally, when you have the ions together, you can go through the step of coalescing together to form the solid. So these steps, they outline what's known as the Haber cycle, and sometimes it's called the Born-Haber Cycle for both scientists. But the idea behind this is that you start with your reactants in their natural states. You first go through the step of changing Na to a gas, then the second step of changing chlorine to a gas without the bonds, so not the molecule, now you have the atom, changing sodium to an ion, ionizing it, changing chlorine to chloride through electron affinity changes, and then bonding the two together, the opposite of the lattice energy. Now, lattice energy, they really don't ask you much about this 5-step Haber cycle, but what they do talk to you about is what changes the size of the lattice energy. And so to just give you some examples of that, if I were to have something like, NaCl, and I were to compare this with something like KBr, well, Na and Cl, these are smaller, and these are larger. So the first thing I look at is the size. The second thing I look at is the charge. The charge of Na is plus, Cl minus, K plus, Br minus. So they have the same charge. And so when I look at these two, the smaller the ions, the stronger the lattice energy. What does this translate into? This translates into higher melting point. So this is based on Coulomb's law, where the force of attraction is equal to the constant times the charges, which in this case were +1 -1, over the distance squared. The smaller the distance, the greater the the greater the attraction. The greater the attraction, the higher the lattice energy. The higher the lattice energy, the higher the melting point. What if we were to change up the charges here? What if I were to do, NaCl versus magnesium sulfide? Well, now they have pretty much the same sizes because they're all in period 3. But this is +1 -1, and this is +2 -2. So this greater charge, again, now you're going to have stronger lattice energy due to the higher charge. You're going to have an increased melting point. And that one is due to the charges up top here. So, practice for Lewis structures we're going to do in class. What I wanted to briefly talk to you about in the next few minutes is get you started with covalent bonding. So this is showing you some covalent bonding between two chlorine atoms. The two chlorine atoms bond by sharing electrons. The bond between the two chlorine atoms is called a shared pair, and these ones out here are called unshared or lone pairs. We're going to spend most of our time talking about covalent bonding for the next few weeks. This is when you have two nonmetals. Sometimes there's a metalloid thrown in there. In either case, they have similar ionization energy and electronegativity, so they're forced to share electrons. When we form a covalent bond, it's because the nuclei are attracting the electrons in the bond. There's also repulsion going on, but there's a balance between everything. We have a balance between the sharing of the electrons between the nuclei and the repulsion of the electrons by each other and the nuclei for each other. Now we could share up to 3 pairs. We have a single bond, we could have a double bond, or we could have a triple bond. This is showing you again an illustration of the repulsion and the attraction. So the nuclei repel each other, the electrons repel each other, but in the end, it's the attraction for the electrons by the nuclei that hold the 2 atoms together. This is showing you a method of looking at it in terms of electron clouds. Now, just to give you an idea, if I were to graph this out for you using axes, and this was distance, and this was energy, 2 atoms out here, they are far apart from one another. Their energy is essentially 0. As they get closer, they start to attract, and the energy will dip down, and it will reach a point that's a minimum in energy. And right here, right at this point, this is where I have my stable bond. If I try and bring the nuclei any closer together, the energy will shoot up like this, and we'll end up with an unstable bond. So this point right down here at the bottom, this is my bond here. This is where I have my atoms bonded together. Okay, so what I'd like you to do and stop with is Lewis structures. I want you to really read these over and go through these in detail. Because tomorrow when we go into class, I'd like to talk to you about these rules. I'd like you to look at all 8 of them, and I'd like you to know them. So that tomorrow when we get to class, and I ask you, what's the rules? What's rule number 1? What's rule number 2? What are the steps for drawing a Lewis structure? You would have done it. Quickly run through one of them with you. Let's say I did PCl3. First step says to count up the total valence electrons of all the atoms. These add up to 26 valence electrons. Second step, put the atom there's less atoms of in the center. P goes in the middle, the Cl's go around it. Step 3, which I already did, I place single bonds between the atoms. Step 4, I make all atoms have an octet. The exceptions we can go over too, but I'm going to give each one of them 8. Cl already had 2 in a bond, I give it each one 6 more. P has 6 in the bonds, 2, 4, 6 in the bonds, I give it 2 more. Step number 4, make sure they all have an octet. Step 5, count electrons. Make sure electrons in the structure match the original. So I count up all the electrons. I want to make sure they have 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I'm done. This is a correct structure. Sometimes, though, you'll count them up. And guess what? You'll have too many. I'll count the structure and I'll have 28. And when I have too many, I'll need to form a double bond and redraw it. So I want you to practice a few of these tonight. Follow the rules, take your time doing it. I'll give you 3 to do. Let's try something like SO2. Let's try something like CO2. Let's try something like HCN. All right, give it a try. Let's see how you do. I'll give you one more. Let's do OF2. And tomorrow we'll go over this. We'll go over Lewis structures for ionics, and we'll be in good shape. All right, have a great day, and talk to you soon.